you know, how do you top that? I just don't know. So maybe to top that, we'll just introduce the man who's going to do this, and so maybe we'll kick things off, and it's a real pleasure for at least the third time in this seminar series to introduce Dr. Egor Dontsov, and Egor currently works at ResFrac Corporation, and at ResFrac he focuses on simulator development, and in particular he's recently improved hydraulic fracture propagation logic, and he's working on the dynamics of proppant in a wellbore. Now, previously, Egor worked at W.D. von Gotten Laboratories, and he was on the faculty at the University of Houston. He has over 50 peer-reviewed journal publications and over 20 conference papers, most of which are related to hydraulic fracturing and proppant transport. And Dr. Dontsov, thank you so much.
All right, thanks, John, for the introduction. Let me share my screen so that and you confirm that you can see it. Are you guys able to see my screen?
Yes.
Okay, full screen. Just make it a little bigger. You guys, all right. Okay, thank you, John, again for the introduction, and thank you everyone for coming. I apologize, I'm a little bit, sick today. I'll be like coughing probably a little bit, so that's life, kids in daycare, for those who know. But anyway, let's try to make it fun, and let's all learn something new today. And so today I'll be talking about something which I worked on for maybe last 8 months. I guess I started about 8 months ago, and this is a relatively new topic for me, but it's very exciting, very actually rich, physics rich topic. So it's about perforation phasing and how perforation phasing essentially affects proppant transport in the wellbore and where it ends up being, for different clusters. So to give you an idea, so here's the problem. I mean, there's basically the same problem here shown under, for different, basically different schematics, right? So we have a horizontal wellbore or near horizontal wellbore. So we inject certain slurry flow rate and proppant flow rate, and then we have a stage, right? So we have a stage, basically we have several perforation clusters, and each cluster has several perforation holes. So basically exit points, right? So we essentially have holes in the pipe. And then you have a plug at the end. And so as you pump the slurry and proppant, the question is, where does slurry go and where does proppant go? Okay, and how perforation phasing affects the result. So that's the particular thing. And so this is kind of like a cartoon from modeling point of view. There's another cartoon also from previous studies from modeling point of view. Again, you can see the different perforations have different orientations. And of course, we have gravity, right? So it's going to affect the result. Here we have laboratory scale setup. It's more like, so here, see, you have like 6-foot cluster spacing here for clusters. Again, you have a bucket attached to every perforation hole just to measure the amount of fluid and proppant that comes out. And here on the right, we have field scale setup from Snyder. Again, it was all, all these relatively recent publications. So where you have a field scale stage lengths around 200 something feet. You have, I think, they had several test cases. I mean, we'll come back to it. So you had like I think 7 clusters, some had 13 clusters. And so again, you have real perforation clusters, real perforation guns we used, and then they essentially collected sand and fluid which comes out the wellbore in these different containers, right? And then they presented the results. So that's the problem, okay? So we want to model that first of all. We want to create a model to calculate where proppant goes and where slurry go, right? And the second thing, then we want to use this model to optimize. So we want to answer the question is, where should we put our perfs? And at the top, at the bottom, on the side, or maybe put like 6 perfs as shown here with 60-degree phasing. So which one is going to be better? Okay. And again, we're going to focus more on proppant because for slurry, if you use a limited entry technique, right, then we have nearly uniform slurry distribution of fluid distribution between the perforation holes. So we focus more on proppant. Okay, so from the modeling point of view, there are actually 2 sub-problems, okay? And this is actually very important to understand. So the first problem is as proppant travels along the stage, again, this is like a wellbore cross-section exaggerated vertically, quite a bit. So right here, when we pump at I don't know, 90 barrels a minute. So whatever the typical rate is, so pretty high rate. Then the slurry velocities here, again, if you do the math, is about 20 or 25 meters per second, or maybe about like 45 miles an hour. I mean, if you're in Canada, maybe it's like 70 km per hour, right? So it's pretty fast. But the thing is, because we travel so fast here, the particles are suspended. They're well suspended and they're very uniform, vertically. But as you start losing fluid, as you go, lose fluid from cluster to cluster, things slow down considerably. And what happens is particles start to settle. Okay, and so towards the toe of the well, we have a lot of particles settling. Okay, and again, it depends on particle size and so on and all other parameters. But nevertheless, the ability of the flow to suspend particles reduces a lot. Okay, and so what happens now, you have a situation like this. So now if you have perfs at the bottom, they're going to be grabbing more particles because they all settle. But perfs at the top are going to get less particles because, again, particles are settled. So the concentration locally is much less at the top of the well. So that's the basic reasoning why phasing may be important because of particle settling. Okay, so that's the first problem. And actually, this problem is not well studied. I mean, what I found in literature. So this is not. I mean, recently people realize it, but it's like only recently, maybe within like last year, maybe two. But the second sub-problem actually been around for a while. I think one of the first works was by Sharma. Even before that, there were experiments. I'm going to show it later in the presentation. But it was Sharma did it like in 2016 and so on, and previous experiments were like in the 80s, 90s. So the second sub-problem is related to particle turning. Okay, so again, think about your particle. I mean, it's like very similar to driving the car. Okay, and so as you drive this car, again, at 40 miles an hour, now you have to suddenly stop and then turn, within like a few inches or a few centimeters. And so what happens is that because particles have high mass density, they tend to, miss the perforation. Basically they flow by. And so what happens is that we lose some fraction of particles during this particle turning phenomenon, right? And so that's this thing like always reduces the amount of particles we're getting. And again, it depends on particle size and other parameters, how fast you flow and so on. So if you have very small particles, they're easier to turn. If you have like gravel particles, they're all going to fly by, right? Just to give you the idea. So this is the second phenomenon. And also just to add on this, like in the model, so what happens is that see you have this is like your wellbore cross section, right? Another very important concept is that so you put your perforations so somewhere here, just example of single perforation, and that you have your total rate here, the total amount of flow rate of slurry flow rate through this cross section, for instance, like 60 barrels a minute, and that 2 barrels a minute go into perforation. And now if you have uniform velocity profile, that about 130, right? Because 2 barrels or 60 of this area go into perforation. It means so particles only next to perforation, a certain area which corresponds to 1/30 of the total area. For this example, is going to go into perforation. In other words, you're grabbing particles and slurry and fluid next to perforation. Okay, so if perforation is at the top, you're grabbing particles at the top. Perforation is at the bottom, you're grabbing particles at the bottom, right? And then here's again schematics of so-called fluid ingestion zone. So again, if you imagine the fluid streamlines, so fluid from this zone enters the perforation, and particles from a smaller zone enter the perforation because those are a little outside. They miss again due to this inertia. So that's the second problem. Okay, so we call it the particle turning problem. And so they work together. So let's go to the first problem, right? Again, it's, as I said, it's pretty overlooked in petroleum industry at least. But I found this very nice PhD thesis by a guy from Canada in 1993. So he was studying the sediment transport, so like more general, not oil and gas related. And so he had this loop, right? And so he pumped slurry and observed the variation of particle concentration in the vertical cross section, okay, and the velocity as well. And so he did like 73 cases total with different particle radius, from very small kind of like proppant, sand, all the way to gravel here. different pipe diameters, different particle volume fractions, and different average velocities. Oh, and I forgot to mention that all this actually happens with fully turbulent flow, right? Because of the velocities at which we pump, that's so high, so the flow is fully turbulent. So we're talking about the modeling of, or in this case, experiments of slurry flow or particle flow during fully turbulent flow, right? So this, and turbulence never makes things easier. It only makes things more complicated. But in any way, so to give you an idea, so here's like an example of the measurements for these cases, 62330, I just picked this 3, the good ones. And so that's how the particle volume fraction here, phi, varies in the vertical cross section. So you see, again, depending on parameters, you can have more or less uniform particles, so they're fully suspended. And as you slow down, now you start having, or maybe, you change pipe diameters, the other things, right? Particle size. Now you start having this kind of behavior where you have really not a lot of particles at the top, and then quite a lot of particles at the bottom. And the model that we developed actually, it matches this thing pretty reasonably. And I'm going to say just a few words about the model, just in a second. Be patient. And here on the right, we plot in the velocity profile. So again, so what happens is that for turbulent flow, if particle distribution is uniform, then we're going to have kind of constant velocity profile. But because we have more particles at the bottom, now we have kind of this profile where things slow down towards the bottom because you have a lot of particles at the bottom. So that's how the general solution behaves. Okay, and then things depend on the parameters. And just to give you an example, so I hope you can see here clearly on your screens. This is screenshots from lab experiments, and you can see, again, you can see basically, so if you pump relatively, at a relatively low rate, you have more particles hanging out here at the bottom, right? You have high concentration, and then if you pump higher, now you have more uniform concentration. So again, so this is the experimental view of this result. Okay. And then, so I'm going to add just a little bit on the modeling. Again, I cannot go through all the mathematical details. For those who are like math enthusiasts, I want you just to give you the main idea of what's in the model. Okay, and so what's in the model is very basic physics if you think about it. So we want to have equilibrium condition for particle pressure, because when particles flow in this pipe, they interact. And you think about like gas molecules, right? So as they flow, there's certain motion, like not just along the pipe, but also perpendicular to it, kind of like temperature-related motion. And so this creates particle pressure, okay? And so now this particle pressure has to be in equilibrium, right? And so it happens. So the main equation that you have the pressure gradient equals to this hydrostatic pressure gradient, right? So we have gravity force, we have buoyancy force, and then phi is volume fraction. So this is the main, the main equation. And this on the right is basically the settling. So if we are not in equilibrium, right, then what's going to happen that there's going to be particles will start to settle. And so this is a settling term based on essentially Stokes law with effective viscosity, because again, things can be turbulent. So that's the main idea. And also the particle pressure is proportional to horizontal velocity squared. Just like for, again, if you look for kinetic theory of gases, so we have the temperature and pressure, they're all proportional to the average, the mean square velocity, right? So that's the same idea. But what it means is that, you see, because we have this velocity dependence, if you go really fast, now particle pressure is high, right? It's really high, and so this gravitational gradient becomes relatively small. Now everything is uniform. As you slow down, now the overall particle pressure reduces, and now this becomes meaningful. Things settle. So that's pretty much the main physics. And again, I have a references, at the end. So if you're interested, you can, you can read in all details. Well, let me show you how the solution behaves. Okay, and so here we have, so essentially the results depend on two parameters. So one, I call it dimensional gravity, but I think also related to Schill's number or inverse Schill's number. So here again, 8 is number, Vm is the maximum volume fraction, density contrast, gravity acceleration, wellbore diameter. This is another like constant, fluid density and velocity squared. So the main thing is almost everything is constant except this velocity squared, right? So again, so if we if you're at the hill of the stage where velocity is high, now this parameter is small, so we are right here on the left side, which means the volume fraction, the vertical cross-section is constant, velocity is constant. Again, this is like two-dimensional cross-section. Again, everything is the same color, so there's no settling, everything's uniform. As we slow down, this guy increases, we go to the right. Again, we start seeing the volume fraction, looking like this. So basically particles settle. The velocity again slows down in this kind of bed-like view. And then into like two-dimensional view, that's how your wellbore cross-section looks like. Again, you have a lot of particles at the bottom. It's basically almost forming like a bed. So everything, whatever you have, is almost settles. And like in this limit, like about 1,000, this dimensionless parameter, now we pretty much have like a bed, and which almost doesn't move. Okay. And I should warn you that here the model assumes fully turbulent flow, right? And so once you start going to this side, you start violating these assumptions because you slow down significantly, right? So probably we shouldn't use kind of model like in this limit. Okay. So, and the second parameter I should say is the time required to reach the steady state, which is your settling time, because what happens is that as Slurry travels along the wellbore, it hits the perforation, hits perforation cluster, then it suddenly slows down because it loses the flow rate. But it takes some time for particles to reach the new equilibrium. So say to transition, say from this solution to this solution, and we have this, the time scale for this as well. So this again, there's two parameters, and the thing is, if particles are big, now this transition time is quick. If your particles are really small, then it takes a while for particles to settle. So that's the basic physics in here. So let's go into this particle churning subproblem, okay? And again, as I said before earlier, at the very beginning, right? So very two important concepts is this, like this ingestion zones, right? So basically, the idea is that we grab in fluid from certain area around perforation, and the proppant we grab it from even smaller area because particles tend to miss the perforation. And here on the right, I show you some examples of CFD simulations which actually confirm that, right? So this is an example of CFD simulation. You have a wellbore cross-section, color shows proppant concentration, and they actually plotted the streamlines for fluids here and for proppant. Because in the model, I assume that this zone is circular, and then here the CFD simulations show that, well, they are circular, so it's like a very good assumption. And also here the thing on the bottom shows that this circle, the size of the circle changes, as we go from heel to toe. The reason is because, again, at the heel, again, if you pump like 60 barrels a minute, and now in the perforation, you lose 2 barrels a minute, then the area of this, total, zone where you have the streamlines is like 1/30, small. And towards the toe, your total rate now is not 60 barrels a minute anymore. It could be maybe, like 2 or 4 barrels a minute. So if you have like 4 barrels a minute and then 2 barrels a minute go into this cluster, into this perforation, then you grab in proppant from half of the area, right? So that's the idea, right? So that's why the size changes as we travel along the wellbore. And again, for mass enthusiasts, I'm going to add just a little bit of equations to make sure you guys understand what's the mechanics behind it that is in the model. So the idea is the following. So we consider mostly the horizontal motion of a particle, right? And so as we start slowing down, essentially we start accumulating slip velocity, right? The particle starts accumulating slip velocity because fluid slows down, and then particle has higher mass density. And so what counteracts this thing is the drag force, right? And so that's what this equation is saying. So we have this acceleration sorry, due to, again, so your slip velocity acceleration, right? And then we have on the right side, we have the driving force, which is fluid deceleration, because fluid has to stop in order to turn. And we know, again, we basically estimated based on scale, just velocity over time. Then we have a drag, and we can have laminar or turbulent, right? And so basically, then this equation can be solved analytically for all the parameters, and this is going to give you the the main result. And as I said, also for the ingestion zone, again, if you have constant velocity profile, then you can just take the ratio of the areas, just to calculate the area of this ingestion zone or the size. So we take the ratio of the rate into perforation to the rate in the wellbore, and then it should be equal to the ratio between kind of this area and the wellbore area. But if you have velocity distribution in general, you have you can write the same but in the integral sense, because things vary a little bit vertically. But anyway, this is the main concept. But I really want to focus like on this one, that again, so the particle essentially, so the driving force again is density contrast, it's fluid deceleration, and then what counteracts it is a drag force, which is laminar and turbulent. And like this slide again shows the parametric space and where can we be, you know, like in this parametric space based on the parameters, right? So the thing is, what can dominate thing, right? So there could be an example where you have, like, if your particles turn very quickly, or think about if you have pretty large particles, so that the drag coefficient is neglected. So in this case, so I call this this inertial limit, right? So inertial limit, and so it's if this is dimensionless time, again, I don't want to go into the details, but the main idea is that like this term dominates, so the drag is not important. So when you turn, so it's like there is no drag, no viscosity, right? And so it happens that if you are in this limit, you have no sensitivity to viscosity, right? No sensitivity to particle size, because it's all related to drag. And vice versa, if it takes a lot of time for particle to stop and to turn, now that things become drag dominated, and now you're here on the right. So in this case, now you start having sensitivity to viscosity and particle size, okay? Because again, what we want to say, we want to understand where do we have, for what parameters we have sensitivity to particle size, because people may say, okay, I'm going to pump smaller proppant and it's going to solve all my problems, right? But the answer is that it's not always going to be, it's not always going to solve all your problems, because there can be cases where there is no sensitivity to particle size, okay? Or people may say, you know what, I use a thicker fluid and it's going to solve all my problems. But again, if you are here and your drag terms are not important, then good luck with that, because there is no sensitivity. And also within drag, so the vertical axis, your particle Reynolds number, again, depends on the parameters. You can have turbulent drag dominated or viscous drag dominated. So if it's turbulent drag dominated, again, your viscosity is not important, and your particle size dependence is relatively modest. But for viscous drag, now we have higher dependence on particle size and dependence on the viscosity, right? So the bottom line is, depending where you are, this allows us to understand what sensitivity we have to viscosity and particle size for this problem of turning. And let me give you an example, why is this important? I know it might be a little hard to follow, there are a lot of parameters and so on, but just let me give you an example why this is important. So here's an example of CFD simulations for examples of the particle turning problem from Sharma. Yes, it's Sharma, right? And so what they show is that there is almost no sensitivity to viscosity. So what we are plotting here, just to make sure you understand, so the horizontal axis is the ratio of slurry flow rate, so this S for slurry, through perforation over slurry flow rate at the inlet or upstream. Okay, so you pump, like 60 barrels a minute here horizontally, 2 barrels a minute goes up. So this is like 2 over 60, right? So this is the ratio of slurry. And the vertical axis is the same, but for proppant flow rate. So the fraction of proppant, that exits through the perforation. So if we are on this dashed line, 1-1 line, it means, this particles are able to turn perfectly. And because we are below, it means we are losing some proppant, some particles miss the perforation. And here they use CFD simulations. Again, we compare it to the model as part of our calibration procedure. But nevertheless, they use different viscosity, 0.1 centipoise, 1 in 100, and observe almost no variation with respect to viscosity. Okay, and why? And the reason why, because if you plot them on this diagram, they're all very close to this inertial regime. So the particles turn really, really quickly, for the parameters that they use, as shown here. And there is just basically not enough time for drag force to kick in. And so therefore, and also they're close to this turbulent zone. And so once you're in this T zone, now again, this turbulent drag, and turbulent drag doesn't depend on viscosity, right? So that's why we see almost no variation with respect to viscosity, and then you change it like 3 orders of magnitude. Here on the bottom is experiment from the one of the first papers working with this, from 1982. There was a vertical well, and so there's no effect of gravity, and so they analyze the same thing, the fraction of proppant that goes through the perforation, and here we have pretty strong sensitivity to viscosity, or at least observable, and to particle size. And why? And the reason is because these points correspond to these kind of circles, which are close to this drug-dominated case where viscosity is important, right? And so that's why we have sensitivity to viscosity, right? And so that's the idea. That's why we need to plot this kind of this like universal parametric space just to better understand this seemingly contradictory results, right? Because when you first look at it, it doesn't make sense, right? Because and it was actually the same as particle size. You look at Sharma's results as particle size. There is no dependence on particle size. Whatever proppant you put in, it's going to be all the same. But here we see sensitivity with particle size. So that's really important to understand. So this is the last relatively complex thing, and then we start having more fun sort of things, comparisons. But please be patient with this one, because this is also very important, because the whole problem of particle or of slurry flow in the wellbore can actually be drawn or schematically represented on this parametric space, because there are two main parameters. Okay, so again, there are two subproblems, and so there is one parameter per subproblem. So the x-axis is this dimensionless gravity, right? So if we are right here, we are fully suspended. If we are here on the right, we are fully settled, right? So and as we go from left to right, so we, as slurry slows down, so essentially we have more particle asymmetry in the wellbore. And the vertical axis is turning efficiency. Basically, we want to understand what fraction of particles is able to turn, right? So if turn efficiency is 1, then everything turns. So essentially, if you go to this plot, you see, so if you're like on this line, turn efficiency is 1, and here we are, so if this is vertical is 1, so here we're about 60%, right? So we lose 40% of proppant. So this is turn efficiencies. So if you're about 60-70%, so you're going to be right here. It means 40% of particles are unable to make the turn. And so conceptually, we can outline, the limits where we're going to be depending on the parameters. For instance, if everything is uniform in the wellbore, so we pump really, really high velocity, and particles are able to turn because, for instance, they're very, very small, then everything is uniform. So the proppant distribution between clusters is going to be kind of flat line. So every hole is going to get the same amount of particles. At the bottom is the limit, which practically never occurs in the field, but still it's important to understand. So basically, when turn efficiency is 0, it's when you start pumping gravel, right? That's physically, that's the limit. So in this case, you have, and as you fly by the clusters, the first cluster gets nothing because again your turn efficiency is 0, and then nothing, and eventually the last cluster takes whatever remains in the wellbore. I mean, practically it's probably going to screen out, but again, for the sake of this limit, that's kind of the limit. So I call it last cluster takes all, because you get nothing, and then you get whatever remains for the last cluster. And here on top right is called phase insensitive, because again we have modest or relatively high turn efficiency, and then you have a lot of settling. In this case, again, if you put a perforation at the top, you get no proppant. Perforation at the bottom gets a lot of proppant. And so in this case, we can have more complex scenarios. So for different phasings, we have very, very different results. Okay. And now let me show you just a few examples, like from lab scale and field scale. I'm going to show you where we are in these parametric spaces and what is important, what is dominant, and so on, and how we compare, the model. How does it compare with lab data? And I should also point out that the model was actually calibrated for the two subproblems independently. And so what I'm showing right now is actually the comparison. There is no calibration to this data. So the first thing is this experiments where with 3-cluster geometry, okay, 40-70 sand and 4 perforation with 90-degree phasing. And now we have 1 tank per cluster. So here we show proppant volume fraction versus perforation number, okay, for different wellbore velocities, from low velocity to high velocity, okay. Now, here in the model, we show the proppant concentration per hole, for each perforation. In the experiment here, they collected, the proppant from all perforations, and so it's essentially the average of the cluster. And so the black line shows the cluster average for model, and the red one shows for the measurement. Okay. So what we can see overall, we have a decent agreement, and then for low velocity, so we have kind of a little high concentration for the first cluster, and then kind of lower for the last one. And as we pump higher velocity, with high velocity, then the trend is very different, right? So qualitatively different. So we start with a little bit lower lower concentration or lower propant received per cluster, and then transition to higher. But what is really striking is if you look at the amount of propant we get per hole in the model. So first we have hole at the top, we get nothing. On the side, we get something. At the bottom, we get a lot. And then on the side, again, we get something. And so this trend continues. So even though we average okay, the actual distribution per hole is vastly different. It's really very, very different. And then if you look at these diagrams, so the turning thing, right? So again, we go from left to right. So as we are on the hill cluster, so we're nearly in the inertia regime, meaning that the particle size is not really relevant. And as we slow down, that's when viscosity kicks in. So we're roughly in the middle. And then for turning efficiency, again, it's about 70%, 70–80%, like for this sand. I'm going to show you for different sands. So you see, these things varies. And the dimensional gravity is kind of spans again. So we're not fully uniform here on the left, but we're not yet super on the right. But we're kind of in the middle. But still, we have very strong settling. Like for around 1 or 2, we have relatively strong settling, and that's why we see various variation of propant per hole. Okay. Now they have comparison with similar experiment from similar authors, but now they had different tests, and now they have a bucket per hole. Okay, and so the first test has 3 clusters, and then there are 2 that had 4 clusters. And the thing is, now we can compare the measurement for each individual perforation to a model, right? So this we need to compare the circles, the red circles, to these gray squares. And again, it also had 90-degree phasing. And so again, we have the side perf, then top perf, side perf, and bottom perf. And they use slightly different parameters and so on. But we can see that we qualitatively, and quantitatively also pretty well match the lab data in the model. I mean, not perfectly, we have some disagreement, but we match pretty well. So the first test 1 was tap water. Test 2, test 3 were HVFR, pretty high viscosity. You can see everything is pretty much uniform. So this is actually not very interesting case because you are like exactly in this U kind of vertex, if you wish. So everything is very uniform. So, but it's very exciting to see that we actually, again, we don't calibrate against this data. We actually, we just compare. We calibrate against previous, experimental data for subproblem 1, subproblem 2, and yet we match it pretty well. The last big test is related to field scale measurements. So from Snyder et al., they actually used 3 tests. So they call them PTST1, PTST2, and PTST3. So the first test, they had things here, so 8 clusters, 6 perforations per cluster, 60-degree phasing. And they use different mesh, 100 mesh, 40/70. PTST2, 13 clusters, 3 perforations, phase 120 degrees, kind of like a Y-shape thing. And then the last, again, also 2 propants. And the last case had a bigger propant, 30/50 mesh, and had 15 clusters with 1 perforation located at the bottom, right? So it's 180-degree phasing. So it's a little messy here and hard to see, but sorry, but essentially for 100 mesh, things are pretty much flat, from both field scale measurements and the model. We have kind of this nice, not nice, but like a feature where things can start going down for the last clusters for these PTST2 cases, and we have it both for 140/70 mesh. But I really like this case, 30/50 mesh. It's a little cleaner, there are less variation, because here again, what we can see is that in the model, we instead of averaging, on top of averaging, we also plot per hole, and per hole variation of propant really varies a lot, and so this makes all this mess. So again, so at the toe, the last third of the stage, you have really strong variation in terms of amount of propant we get per hole. Okay, but here we have only 1 hole, and it's located at the bottom, and so we can see first the upward trend and then the downward trend. Okay, and so in order to explain this again, so at the beginning, so here everything is suspended, right? And so we receive less propant just because of this turning problem. right? So our turning efficiency, again, if you look at this thing, is about 60%, for circles for this PTSD3. So we'll lose 60% of Proppant, right? So we are less, right, in the model, right, relative to the average. And then as you get less and less Proppant for the first cluster, now your wellbore concentration increases, and now you start getting more and more and more. And then things start to settle right here towards the end, right? And because things settle and your perforations at the bottom, you're taking more Proppant than average in the wellbore. And so that's why you can see this almost like exponential growth of the concentration per hole. But then, because you're getting more and more Proppant from the wellbore, you basically run out of Proppant in the wellbore. And because you start running out of concentration in the wellbore, now you start going down. And so that's why you can see this kind of, this thing. And we match, nicely, the trend with the measurement. Again, in the measurement, we have, variation of perforation diameter, erosion, and other things which are not considered here. But we do match this trend. And also, if you pay attention to this, phasing diagram, especially to the one on the left, I just want to give you an idea that for field scale where we are. So you see, we have 100 mesh here. We have turning efficiency around 80%. So basically, we lose 20% of Proppant, at the hole. And then if you use bigger mesh for a 70, we drop to 70. It's pretty flat. I mean, it goes up and down, but it's pretty flat. And then 30-50 is even lower, so you have 60 or 50% efficiency. And again, if you can imagine, if you use 2040, it's going to be even lower, and so on. And in terms of this x-axis, again, at the hill, where this dimensional gravity is very, very small, so we are fully suspended, and then on the toe, things are really, really settled. So that's basically what, and this is for field data, not for lab. So now let's move on to perforation optimization, because now we have the model, now we understand what's going on. So the question is, how can we use this knowledge to design better clusters, right? So let me remind again, so we have heel here on the toe on the right. And so basically for heel, we have dimensionless gravity, about 1 on the log scale is 0. So we are here at the heel, right? So everything nice and uniform. And we gradually go to about 100 here, so which is here. So again, so things gradually go from here to here, in terms of how concentration behaves. So what do we do with perforations? Well, so what we want to do, I guess, assume that what we want to do, we want to have perfectly uniform distribution of particles per each individual perforation, supporting each individual. And the thing is that for this to be true, the Proppant fraction in the perforation that goes into perforation should be as close as possible to Proppant fraction in the wellbore, right? So again, if you're giving fraction in the wellbore and then you lose you saw some slurry and Proppant in the perforation, but you lose, the Proppant concentration is the same as in the wellbore, then nothing's going to change, right, from concentration point of view. And so if you repeat this process, then everything is going to be uniform. But now we have two competing phenomena. So the first thing is turning, right? Again, so you're losing like 30% of particles when you turn. But the thing is, you have higher concentration at the bottom. And so what happens if you put perforation somewhere, right here or right here, where a little bit closer to the bottom, you can compensate for this, right? You can find a place where your concentration is like exactly like 30% above your average. And so then, it is above, but then because of turning efficiency, it's getting reduced back to the right value. Okay. And so that's, again, that's the main idea. I mean, so I outlined this in this text. So basically, the turning efficiency always decreases the amount of Proppant that enters the perforation. But because we have high concentration at the bottom, and we place perforation closer to the bottom, we can compensate for that and get a little bit more Proppant. Okay. So if you do that, so actually, I plot this, I call this like uniformity lines. So given the efficiency and given how much settling we have for given concentration, like reasonable, at what angle should we push the perforation to be to get exactly the averaging, to get exactly the right amount that we need. And so what happens is here on the left, there's nothing you can do because this 180-degree line, and so you're always gonna be imperfect. But as you go towards the middle, it's about 110, 120 degrees, again, relative to the center of the wellbore. So it's about right here. That's where the optimal concentration is going to be, right? So a little bit below, the middle. And so Now we consider this again field case, which I showed before. I think it was PTST2, and so original phasing was kind of going from 60, 180, and then this is again I use this is supposed to be 300, but I can kind of flip it. I'll make it like from 0 to 180 for the sake of the plot. And so if you do the optimization of phasing in the following way, so you start from the bottom because again you cannot do better than this because again so that's where you get the maximum proppant concentration, and then you gradually kind of transition all the way to the side and about 110 degrees. Then the proppant fraction, again according to the model that enters the per hole or per cluster, is going to be much more uniform compared to this one, much more uniform. And look at there are different scales actually here left and right, and each perforation hole actually gets very similar amount of proppant, but here towards the toe we actually have very different amount of proppant per hole, which means we're going to have different erosion probably. We may have screen out these holes and so on. It's going to be all sort of things associated with that. But then we can go even further. If we reduce the rate to 70 barrels a minute, now we can theoretically make it perfectly uniform with this perforation phasing. Okay, again, it's theoretical. Again, life is different, but still it's a huge improvement, relative to the initial configuration. And then we ask ourselves, what? So we have some uncertainty, right? We have some uncertainty in perforation diameter. We have some uncertainty perforation phasing. We think we put it at 110 degrees, but maybe it's about 105. And how is this going to affect the result? And so what we did, we run like 1,000 realizations because this is actually a very fast model, and even 1,000 realizations, they run within like a couple of seconds. And so we added 10% uncertainty to perforation diameter and 10 degrees uncertainty for phasing. So basically, each perforation hole can have has independent uncertainty of 10 degrees. And we plotted coefficient of uniformity, or sorry, coefficient of variation for proppant distribution at the perforation level. So basically, so we take all the perforation level, like 39 perforations, take the standard deviation divided by mean. So this is going to be your coefficient of variation at the perf level. So we do it for proppant, for slurry, and then do it at cluster level. So basically, when we average over the cluster. And so each simulation, represents a point on this histogram. So we want to see whether this uncertainty actually important or not, right? And then of course we plot the error bars to slurry rate, phasing, and these results. But the number I wanted to pay attention to is this proppant coefficient of variations, but it's 0.63, so 63% variation at the perf level. And once you do the optimization, it drops down to 16%. So it drops down considerably. And again, if you go left and right, sorry, up and down, here, even, so the drop is much more significant than the width of the distribution. Okay, and so therefore, even though if you add uncertainty, which is reasonable uncertainty, well, yes, you make things worse, but the relative improvement that you're getting is much more significant. And also at the cluster level, it's about 19%, and then this is about 9%. So it's still very, very significant improvement. For slurry, of course, you don't have any changes actually because phasing doesn't affect slurry distribution. I think this is the last slide before conclusions. We also wanted to ask the following question. So you know what? You look at this perf design. So your phasing goes from the bottom all the way to the side. Each cluster has different design. It's hard to implement. It's maybe more expensive. What if you have problem with initiation because now you have different phasing? And so maybe some clusters initiate earlier and some later. Maybe some near wellbore pressure drop or tortuosity going to be different and so on. And so they said, okay, what if we want to pick one phasing for all clusters, universal? Then what would this number be? Okay, because again, because this thing runs fast, we can optimize for that. And so when we do that, so we end up about 90-something degrees. And this result is for gun-centered phasing. And if you do wellbore-centered phasing, depends on parameters, but you roughly add about 15-20 degrees. So it's about 110 degrees, 115 degrees if from wellbore-centered phasing. But anyway, so we have much more uniform proppant distribution here. Again, there's some toe bias, we have more proppant in the toe, but still, if you look at these uncertainties, and coefficient of variation, they're still much lower than the original case, especially per perf level. Okay, so that's going to be the more universal answer for this one. So I think that's about it. So time flies when you're having fun. So here's a summary, right? So the first message is that so this problem of Proppant distribution perforated wellbore has two sub-problems. Okay, so I hope it's really clear. So the first is how slurry flows and how it settles, and the second is how particles turn. Okay, and there is actually one more problem which is ignored here, which is perforation erosion. And we, of course, we're planning to add this, but right now it is not there because it's complex enough, at this point. And then there are two sub-problems. So each problem for each problem we developed a model and it's calibrated against available data. And then we compare results to set of lab scale and field scale multi-cluster experiments. Okay, not just flow, not just turning, just multi-cluster experiments. And then based on the model, so we proposed optimization, perforation, phasing. Okay, and so essentially the optimal phasing, again, transitions from the bottom of the well to roughly the side of the well, or if you want to keep or use just one universal phasing for all clusters, so it's a little bit below the side of the well, like about 110 degrees, depending on the parameters, particle size, and so on. So that's where we are. And then lastly, we did uncertainty analysis just to make sure that little uncertainties that we have in the field not going to actually overshadow this improvement by the optimization. So, and lastly but not least, I want to mention that here we assume relatively ideal case when slurry distribution is uniform, right? And so all this optimization assumes the slurry distribution is uniform. So, but if your slurry distribution is not uniform, then it's going to be the primary factor actually affecting where the proppant goes. So the first thing to solve actually the uniformity of slurry, and then once you have that, then this phasing can be used to get more uniform proppant distribution. And so here's a list of publications. So sorry, John, just one last thing. So this archive publication has all the math, for all math enthusiasts, all equations and so on. I think like 50-something pages, like a lot of comparisons with experiments. We have ARMA papers about optimizations coming up 2023, and Nurtek paper about uncertainty analysis also coming up in 2023. Thank you. Now I'm done.
Outstanding. Yeah, really, really outstanding. And Egor, you've generated a lot of questions. We'll do our best to address those. I don't know. Can you see them by any chance, or would you like?
I can. Yes, I can. Let me.
It's probably better if you read them yourself.
Okay. Okay. So the first question from Ed. Does your problem 2 allow for more than one perf at cross-section, assuming you have a finite length along the wellbore for the numerical flow grid? Right, so right now, I assume that there is only one perf for a given cross-section, but they can be fairly closely located, because what happens in the model is that, once you lose a certain rate, right, in the perforation, your wellbore velocity reduces drastically. But again, there is some time for things to settle, for particles to settle. And so if your next perforation is very, very close, so basically what happens is that your particles don't settle, don't have enough time or distance to settle. And so, so essentially in the model, you use the same kind of profile of particle concentration, if you wish. But yes, we assume only one perf in the cross section. Maybe we can improve and do 2. But the thing is, we need to have data, right? And so for all the data, they always do one perf, and so that's so far the best we can do. Okay. Let's see. From Matt Paradise, right? I'm curious about your thoughts on the industry trend towards 0-degree phases. So when we perf only at the top of the wellbore, as it relates to proppant transport and placement. Both problems 1 and 2 would lead to me think that 0-degree phasing harms our ability to put proppant into fractures. Well, yes, actually, I agree with that. So I think they used 0 degrees for some other reason, but this definitely would be seriously suboptimal from this modeling point of view. And the reason is because, so remember when I showed this, maybe actually I can go to this parametric space a little bit more. Come on, load it up. This one, right? So the 0 degree phasing is going to resemble something like this, but not to that extreme, because you'll be getting less proppant initially because of particle turning, and less, and then you'll be starting getting even less because particles settle, and you try to grab particles from the top. So your profile is going to be kind of like this, and then it goes down, and then the last cluster will take a lot, and then it can screen out and can have high erosion and so on. So that's at least what the model tells us. And so I agree. So that 0 degree phasing is not the way to go, because ideally you need to be somewhere in the low, like on the side or a little bit lower side, lower part of the well. Okay, Boole law. Okay, thank you for your presentation. My question is the following. Is it possible to incorporate multi-size proppant, such as a mixture of 40 and 70 mesh proppant into your model? Additionally, how does the use of mixed sizes affect proppant admittance along the wellbore? This is an excellent question, because here in the model, I assume that we have one type of proppant, one size of proppant, one density of proppant, and so on. But in general, I mean, I think, because, well, I should have mentioned that eventually we're going to implement it into RESFRAC, right? And we will have multiple proppants in there. And so, I haven't finished it yet, but the idea is that, I'm thinking already, through this question, because I want to have several types of proppant mixed together potentially in the wellbore, and so the idea would be to track different proppants with different concentrations. Each of them is going to have maybe different dimensionless gravity and different turning ability, but you treat it like a mixture, right? So you have like half of big particles, and then half of them are going to turn, half of them not going to turn, and then smaller particles, say, all going to turn. And so again, because we treat it as a mixture, it should be able to solve the same problem. So, but anyway, it's a very relevant question, and during implementation, this is going to show up, and we're going to do it one way or another. But again, there are no actual experiments on this. Maybe somebody will do experiments. That would be nice to compare. Okay, from Jihao Wang. I'm curious if the cluster spacing has an impact on your model results, because the equilibrium distribution, proppant distribution, will be distributed a bit after the slurry passes by a cluster, and it'll take some time to re-equilibrate before reaching the next cluster. Excellent question. Yes, exactly. But basically, what Jihao is saying is that we have one cluster, say with G equal 10, and then right after this cluster, we increase this G, because we lose some slurry, and so things go slower. And then the question is, do we reach equilibrium by the next cluster? Well, it depends. It really depends on settling time. And what I found from the field data, that if you have like 40-70 mesh size, then typically you reach an equilibrium. If you have 100 mesh size, then you don't reach equilibrium, which is fine. It means you have less settling. We still can model this, so I don't assume that we're in equilibrium. I solve for time transition. I should have mentioned this probably. So it's not like a limitation to the model, but yeah, it makes it's a very good question. And actually, in the lab experiments, it's important to have the approach pipe lengths long enough so that we actually reach an equilibrium. And I found that not in all experiments. Again, just by doing the numbers, and not in all experiments, they had long enough approach pipe lengths to be in equilibrium. So this actually also was a challenge to compare the results. So the next question is long, from Alexei Savitsky. All right, it's a very relevant problem, and then a few questions. Do you account for particles interactions via solid concentration? Yes. Right, so again, because see, we model particles as continuum, right? So we model the interactions through particle pressures, kind of like implicitly. So it's not like we model each individual particle. So implicitly, this is accounted for. Okay, but this is again a continuum model, right? So again, we account through particle pressure. Do you account for increasing velocity at the toe of the stage when the cross-sectional area is reduced due to solid settlement? Yes, it is accounted for, because let me go to this slide, right? And so see what happens if you have a lot of settling here, you reduce cross section, but not by a whole lot. But you see, this is your velocity profile. See, you're a little bit above average. So if average is 1, things are normalized. So right here, you're a little bit above, and right here you're below because you're practically stuck. So this is accounted for like in this fashion, in this fashion. And we do use this velocity distribution as an input, in calculation in the model. So this is accounted for. Third question, you mentioned the rate dropping to 2 barrels a minute at the toe. That would be a poor limited entry design. Do you consider the limited entry design in your model? Yes, I assume that everything actually, again, so going back to assumptions, so everything is turbulent like all the time, even though at the toe, the stage it may not be, not always be the case, but I assume the flow is always turbulent everywhere, even though we have the settling. And I assume limited entry, right? And here I assume no fractures, and like no stress shadow, no things like that. So I assume that we have same perf diameter, plus uncertainty, and so basically your slurry distribution is just determined by perforation friction, okay? And dropping to 2 barrels a minute at the toe, I mean actually before the last perf, right? I mean, because it's roughly for limited entry, you can have like 2 barrels a minute per hole. And so if you don't look at the clusters, as multiple holes, but just before the last hole, it drops to 2 barrels a minute. Okay, that's what I meant. The next question is from Ed. Does the literature have cases where repeated experiments were run to establish the degree of data predictability, concerned that turbulence introduces data scatter that reflects in model mismatches? Very good question, right? So you see, for particle turning, there are some different cases like experiments and CFD simulations. For flow in the pipe, and the settling, there's actually not enough data. I mean, because I found only one good source, and there is no such thing in the petroleum literature. I didn't see it because people like to do that. They want to solve the whole problem at the same time, right? Because what I try to do in the model is say, what, we have 2 problems, solve one, solve another, then combine. But I guess it's hard to find funding to solve each individual problem. I don't know. So basically, people try to solve the whole thing combined, and when you try to solve the whole thing combined, then it's a little harder to differentiate these 2 different effects. But so I agree. Maybe we would actually need some more experiment results. That would be great. But overall, I think we still have a decent number of this multi-cluster results, different lab scale and field scales. So I think we have reasonable agreement, but it would be always would be nice to have more. But I would vote to have more actually experiment results on individual subproblems rather than trying to solve the whole thing at the same time. The next question is from Alexei Savitsky. Are you going to expand the model to account for perforation that would be necessary for practical applications? Yeah, absolutely. I'm actually we're working on this right now, right? And so it's very, very important that because erosion is going to change the slurry distribution because the different holes are going to erode differently, and once you change slurry distribution, you change everything inside for Proppant as well. So it's very crucial. And again, as I mentioned at the end, there is no erosion, but it's my understanding it's absolutely a must-have. Again, I initially wanted to do like all 3 subproblems, with erosion being the 3rd one, but the first 2, have proven themselves to be quite challenging and long, and so we decided to kind of have an intermediate stop at 2 subproblems. The next question from Haiyan Zhu. How about the Proppant concentration during cyclic injection? Do you consider cyclic injection of the mixture fluid in your model? So right now, sorry, I consider constant rate, right, and constant Proppant concentration. But again, once we implemented in ResFrac, the fully coupled hydraulic fraction, wellbore, and reservoir simulator, we'll be able to do everything. So in general, there is no limit, or there is no there is no restriction of not including cyclic injection. So we can pump, we can stop, we can wait for things to settle in the wellbore, we can resuspend them. It all can be modeled. Okay. The next question from Anthony Pierce. how easy is to change the orientation of the cluster, right? So I think this is more for people in the field, right? But I think they regularly do oriented phasing. So if you have like one of the previous questions, like 0 degree or orientation, and I saw cases when they do 90 degrees, right? So kind of like a side, it's very close to what we need. So it is possible. If you want to do sorry, you want to do various design from cluster to cluster, I think I talked to somebody. I think this is possible. It's just more expensive. So the question is whether it's people decide to do it or not. And the next question from Santiago Serebrinsky. Do you have plans for analyzing multiple simultaneous Proppant sizes as in practice? Right, I think I already answered in a similar question before. So the short answer is yes. The next question is from Bo Zhang. 2 questions. So there are so many parameters impact Proppant transport, but we cannot consider them all in the modeling. So optimized Proppant transport obtained based on one set of parameters may not right for other cases. What do you think about the gap between the modeling and applications, engineering applications? Okay, so the thing is, I mean, we can account for as many parameters as we can in the model. I guess if you change wellbore diameter, things are going to change in the model. If you change particle size, things are going to change in the model. Particle density again. But there are certain things like, I don't know, Proppant roundness. I'm pretty sure it's going to affect things to some degree, but it's not in the model. And the question is, how is it going to affect this? And in the short answer, I mean, I don't know. We need to actually do experiments, right? Because all this model is is based on experiments essentially. Again, recall this is turbulent flow of slurry. I mean, the modeling anything turbulent, I mean, it's hard, okay? And so we actually have some calibration parameters in the model. So it's more like a phenomenological model. So it's mostly like based on experiments. And so whatever you want to include, you need to support this by experiments. So that's a short answer.
So last question.
Okay, let's do this last question. Apart from the 2 problems you mentioned here, can you share some other main issues associated with Proppant transport in industry? Oh, that's, I mean, I think perforation erosion. I mean, I would add to this one. I think perforation erosion, I think is very, very important and needs to be included here. And I still think it's, there's some work needs to be done on erosion thing. And again, how erosion varies with phasing, with heel and towing and stuff like that. I think that was the last question.
Yeah, and there's more, and so if you people have questions, just reach out to Egor. If you don't have his email, drop me a note and I'll put you in touch. I mean,
I'll just gonna scroll down all the way to the bottom where my email is. You can guys make a screenshot or just here you go. You can make a screenshot and send me a note.
Very good. Well, Egor, as you can see from the questions you received, this was a fantastic presentation, extremely well received, really outstanding, and thank you so much.
Thank you. Thank you all for listening, guys.
Thanks, everyone.
Yeah. I think you just missed only one question. So.
And it